You only want. I will tell you the problems I have solved. I didn't get much time, but I have solved 3.4.1. No? One, yeah. Do you want me to solve it on the board? Three, four, 3.4.1. Bisa nomor gana, bisa. Ada. I will read the problem. Let f x to y be a bijective function. F x to y bijective function. Let f inverse going from y to x be its inverse. Let V be any subset of y. V is subset of y. Prove that the forward image of V under F inverse. Forward image of V under F inverse is equal to the inverse image of V. Inverse image of V under F. We have to, somebody, when F is a bijection, if you write F inverse V, we don't know whether he is meaning this or whether he is meaning this. Even if F is not a bijection, this makes sense. This makes sense only when F inverse is a function. No? So we want to do this proof. F inverse, this means, actually what this means, forward image of, let me write it what I have written. That must be correct, however I wrote very fast. There can be mistakes. Oh. I have written, let W equals set of all F inverse Y. Y belongs to V. Because V is a subset of Y. So this is assuming, actually this is this one. W equals set of all F inverse Y. Y belongs to V. This is forward image. Of V and F inverse. Right? And want to show that W is equal to, need to show that W is equal to F inverse V. What is the meaning of F inverse V? It is set of all x belongs to x such that fx belongs to V. This is the meaning of F inverse V. Right? whether f is 1 to 1, 1 to. We don't need anything to define f inverse v. Here, however, this is image of f v under f inverse. Actually, it is like suppose you have a function g from x to y, and say you have say subset, say okay v is subset of x, then we can define g of capital V, this v is equal to set of all g little v, such that v belongs to capital V. That is the meaning of GV. Similarly, we have written that is GV. This is exactly, W is exactly that. No? And if you have here another set, say U, yes, U is subset of Y, then you can talk of G inverse U is set of all x belongs to x, such that G x belongs to U. These are definitions. According to him, he writes these two dots. Right? You need to understand that here what happens is when you have a one-to-one function, if someone writes f inverse v, you wonder whether which one he means. No, there are two meanings that way. When you replace by G inverse, you get something here. Here, of course, you have always the inverse. Right? So we want to show that. Is it very clear? There are two. We want to show that this thing. First, let us show that I say let us show that W is subset of f inverse v. The reason I am writing this way, this is, you always write this. I mean, that's the reason now he has to write over the image of v and f inverse. When you are writing f inverse v means this one. If f is of course 1 to 1 and 1 to 1, it's a bijection, then this f inverse v has another meaning coming from the first one. You follow that? Okay, so we want to show this thing. How do you do? Then what should I write? I want to show that. But what is the next line I should write here?
Let f inverse y belongs to W be arbitrary.
No, I want to prove A is subset of B. What is the first thing I should write? Proof. Show that A is subset of B. When I am proving what? Without, how do I start?
We need to show that all the elements in A are in
all these are subset of R. That's redundant. You don't need it. I want to do, suppose somebody is asking you to do A is subset of B. I am asking, in the proof, what is the first line you write? Nothing to do with that. I am just asking you. A is subset of B. What should I write? You need to answer quickly because already 3 minutes past time. If you are going to prove that 2 sets are in given 2 sets A, B, you are asked to prove that A is subset of B. In the proof, I am asking what is the first thing you write in the proof. First statement.
Let X belongs to W be arbitrary.
There is no W.
Ah, on that thing. Instead of W, A.
If you want to write let x belongs to A, you have to know that A is non-integral. Otherwise you cannot write. Suppose x belongs to
A.
A. Similarly here you have to write. You understand? Many people write let x belongs to A. You cannot write it. It's like, I mean, you are not married. I'm going to say let x be your wife. You will say, sure, keep shut your mouth. You are not married. So you cannot write like that. If you want to write like that, first you have to show that W is non-integral. So suppose x belongs to W. Now what do I have to show?
X is an element of F inverse V.
I have to show that x belongs to F inverse V. That's what I have to show. If x belongs to W, W is F inverse like this. No, I said wrong. W is this one, this is not this one. This is the W. Then what do I know? Then thus there it is.
Y belongs to the table of Y.
Y belongs to Y?
Such that
Y belongs to answer, not Y, no V, no. Such that
F inverse Y equals X.
F inverse Y. I wrote here W. Let's put simple W. Can, because you have X, Y, set, no? Such that F inverse Y is equal to W. Right? By definition. I took W belongs to W. What are the form of the elements in W? They are of the form F inverse Y. You have Y belongs to V. Right? Notice that. Now you need to remember what is the meaning of F inverse. You are going from a V Y to X. You have this function F inverse there. F inverse of simple Y, no? Belongs to. That's it. I didn't already. Notice that. W belongs to X and the F inverse Y is equal to W if and only if Y is equal to F inverse W. That's the definition.
Y is equal to FW.
Y is equal to FW. That is the definition. That's how we define the inverse, no, F inverse function. When this is a function, if you take any Y, if you take any Y here, you the F inverse of Y, you say W, here you have Y, W here, F of W must be equal to Y. That's the definition. Y is equal to F of Y equals to W, and this one belongs to it. Sorry, notice that W belongs to X and FW equals Y belongs to B, yes. Right? Y is in B. Clear? Must be crystal clear. Hence, W belongs to X and F of W belongs to V. Must be crystal clear, don't allow me to just fight on the road without you understand. Without you understand. Is this clear? Now, what is this? This way? No, this one. W belongs to X and FW belongs to V. Therefore, what can you say about W?
W belongs to F inverse V.
W belongs to F inverse V by definition. Because here, when you have F going from X to I, if you take some number here, for instance, Y, no, if you take a subset here, V, or U, or whatever, not this one, we say F inverse V to be the set of all X belongs to X, such that Fx belongs to V. This is the definition. This is F inverse V. Right? This as a set, not, I mean, F inverse, this is not the forward image, this is just F inverse V. Now, W belongs to X and FW belongs to V, therefore, so thus, W belongs to F inverse V by definition of F inverse V. Is it crystal clear? Are you on the fence anywhere? Better in the therapy? You have to ask me. Do you understand the question precisely? Because when you write F inverse V, there are two meanings. When F is 1 to 1 and 1 to 2. Because it has an inverse, when you write F inverse V, somebody can think forward image of V and F inverse. Somebody can think for any, whether it is 1 to 1 or not, if V is a subset of the range set, you can define F inverse this way. That is the definition. Any doubt anywhere? Sure. Okay. So, hence, thus, I can say W belongs to F inverse. So, W is subset of capital. This little w, this capital W is subset of F inverse V. Right? W is subset of F inverse V. On the other hand, now conversely, now suppose T belongs to F inverse V. Now suppose T belongs to F inverse V. When I write F inverse V, what does it mean?
The forward image under F inverse.
No. No. Pre-image of V under F. Backward image of V under F. That's the time we write this way. F inverse V. When we write it, that's what it means. But the funny thing is, it even now we have a problem, no? Because if you are going from x to y, if f is a function and if v is a subset of, if v lies here, then when we say fv, this is actually forward image, fv. Here it is not the forward image. So that's why this question is here. Here I wrote f inverse v to that pre-image of v under f. All those elements in x which map to v. That's what it means. So I took, let's say t belongs to f inverse v. Then, what do I know? What do I know?
T belongs to x and ft belongs to v.
Very good. T belongs to x and ft belongs to v. Now we know that, we know that we are going to use the fact that f has an inverse. Hence I can say thus T is equal to f inverse of ft. Because it is 1 to 1, T goes to ft, f inverse of ft goes to f, I'm sorry, T. Where this is ft belongs to v. Hence, T belongs to forward image of v. Now, if T is equal to f inverse ft, where ft belongs to v. Hence, the T belongs to T, let me write in English, belongs to. T belongs to forward image of V under F inverse. Because T is F inverse of Ft. Hence T belongs to this. Therefore, I began from F inverse V. T belongs to F inverse V. Now I am saying T, hence T, I am able to T. T belongs to forward image of V and F inverse. Therefore, F inverse V is subset of forward image of V and F inverse. V and F inverse. Therefore, F inverse V is subset of W. First I showed that W is subset of F inverse V. Here I have shown that F inverse V is subset of W, therefore F inverse V is equal to W. What happens is, whether F is 1 to 1 or not, this always, F inverse V always exists. You have F is a function from x to y and V is a subset of y. F inverse V is set of all x belongs to x, such that fx belongs to V. This is the definition. Pre-image of V and F. Whether it doesn't have to write this thing, F doesn't have to be 1 to 1. Is it clear? The problem here is because one can run to an illusion. When you write F inverse V here, pre-image of V under F, at the same time, there is a Another meaning, no, F inverse V, when F it is 1 to 1, F inverse V is set of all, F inverse little v belongs to capital V. Two different. This one always, this one when F inverse exists as a function. I mean, we have proved that both are the same. You are under clear? Alright, so that is the first problem. Now the next question is I am asking, I got little worried however, when I asked you to prove A is equal to B, I mean again, I guess it is not your fault because this book, he is focusing on certain things, but you have to know some other things. We have to prove A is subset of B and B is subset of A. These are the two things you have to prove in order to say A is equal to B. A is subset of B and B is subset of A. That's how we prove A is equal to B. And when you are writing A is equal to B, if you don't know in advance that A is non-empty, you don't say let X belongs to A, you say suppose X belongs to A. Right?
So can you use the cardinality to prove this?
Cardinality doesn't come here.
I mean, if A is a subset of B,
Yeah.
and we prove that cardinality of A and B are equal, so can we say that A and B are equal?
That's because of cardinalities are equal, you cannot say sets are equal.
Different elements.
Then,
Can
I mean,
Subsets imply, if the sets are equal, it implies the coordinates are
Cardinalities
equal,
are
not the
equal.
other way.
this set 1, 2. This set pizza and roti. Cardinality of this set is 2, cardinality of this set is also 2, but
I mean, A is a subset of B. We know that. If we know
ask your question precisely.
if we know that A is a subset of B,
Yeah.
and we can prove that if we prove that A's cardinality is equal to B's cardinality, can we say that A is equal to?
Yeah, then you can say A is subset of B. You prove cardinality of A is equal to cardinality of B. Can you see? No. You cannot see. You cannot see. You understand his question?
Yeah.
He is saying, but he is asking a good question by the way. We want to prove A is subset of B. I told you what you have to prove is A is subset of B as well as B is subset of A. So we got the impression that he is asking when if you have two sets with the same cardinality, we can say whether two sets are the same. We reply no. Now he is asking a different question. We have proved that A is subset of B as well as cardinality of A is equal to cardinality of B. Then he wants to know whether we can conclude A is equal to B. No, because if you take set of all 2n, n belongs to n, whatever, we said plus o, and set of all n belongs to n, set of all n such that n is an integer, whatever. This set is subset of, set of all even integers is a subset of set of all integers. They have the same cardinality. But you cannot say set of all even integers is equal to the set of all integers.
But if A and B was finite, then
Then you can say. Then he has to add that also. He has to add that also. Anyway, that was a good question he asked. Another thing that you need to know before I go and look into the problem. Can you see? Because of the book, the places for which I should have paid attention is not given that chance because we are talking about A++. Like that. You need this? Okay. Hmm.
You can go the other way around also, no? With this question, if A is a subset of B and the cardinality of A equals cardinality B, and if A equals B, then A and B should be finite. No?
What? You are saying A is equal to, no, not A is equal to B. We
A
know
is a
that A is a subset of B.
Uh,
Cardinality of A is equal to cardinality of B.
yeah, if those things are true,
Oh yeah.
if it implies A equals B, then A and B should be finite. No? If it's given that if A is a subset of B and cardinality of A equals cardinality of B implies A equals B, then A and B should be finite. No?
I'm not getting that.
There are two of implication. Suppose the implication.
You have to,
Yeah.
because you have to tell me precisely.
Yeah. If the implication A is a subset of B
If
and
A is subset of B,
yeah and
then
cardinality of A equals cardinality of B implies A equals B,
then A equals B.
yeah. If that implication is true,
Mm-hmm.
then A and B should be finite. No?
Then A and B should be finite. Issue 16. A, you are saying, if A is subset of B, n mod of A is equal to mod B, then A implies B. This statement is true for some two sets A and B.
Yeah.
That's what we are saying. Then you have to conclude.
Yeah.
Then this statement again, now if you are saying if this,
Yeah.
then that's why I am saying always you have to write precisely. Then
A and B are finite.
you are saying if A equals B, this is
Yeah, two
this one,
implications.
so two, this is I cannot really say at once if A is subset of B, because this is a conditional statement, no, then A, B are finite. No, I will not answer that now because I am going to be puzzled about it.
Set එක මෙන්න. Set එක මෙන්න. එතකොට set එක මොකක්ද?
If A is subset of B. Because when you put a conditional statement like this, it's very dangerous. Anyway, I will reply to that also next day because this is a dangerous statement. Because here, antecedent is again a conditional statement. Huh?
Yeah.
Antecedent is a conditional statement. What I was going to say is something else. You have X, you have Y. This is something you need to know. X, Y, you have a function F. Then you take any set here, A, let's say A is subset of X. Then A goes to something here. This is FA. Then when you come back, if you take the pre-image of FA, that is F inverse of FA, it is always like this. A is subset of F inverse FA. Because under A you go, here there may be many other things outside matching to FA. It goes other way around also. Let's go to that next problem and see whether you want me to do it. 3.4.2. 3.4. Want to do it or no? I guess that kind of thing I do, no?
It's better if you did it, in my opinion.
Better not to do.
Better if you did it.
Okay. Question is, I guess, question says, let f x to y. You have f going from x to y. And let x, y, S be a subset of x. S is subset of x. And u is subset of y. This is 3.4.2, I guess, yes. Then what, in general, can one say about F inverse Fs and S? What about F of, this is one question, F of F inverse U and U? One problem is what I told you over there, this part. So I am going to do that. It's very simple. But you need to know these sort of things. When in an analysis class, these are the things at the very beginning should be emphasized. But we have emphasized this. Excellence and so that's the problem. Okay. So, in general, we start writing in general, plain. S is subset of the way I told you, no? Here is capital X, here is capital Y. You take S here, it goes to Fs. Then when you come back, it can get bigger. So I am saying S is subset of F inverse of Fs. That's what I am saying. From the picture, you get that impression, I am sorry, not the illusion, the impression. So we are going to prove it. Proof. What is the first statement I should write here? I want to prove this set is a subset of that set.
Let set S be arbitrary.
I mean, I have taken, okay, that is also true. So, when I write like this, I mean, you are in a way better than me. What this is, how, no, he has given let S be a subset of X. It is given. Then we don't need your statement, otherwise it would need.
Suppose that S is non-empty.
Then yeah, that is also too much. So what should I write?
Suppose simple S belongs to capital S.
Suppose simple S belongs to capital S. Then I want to prove that simple S belongs to this set. No? Suppose simple S belongs to. Then what do I know? Then forward image of simple S under F belongs to forward image of capital S under F. If S belongs to S, then Fs belongs to Fs, right? Since S belongs to X, because capital S is a subset of X, no? Since X belongs to X, and if little s belongs to F big S, what can I say? Simple S in capital X. Fs belongs to that thing. What can I say? We have
S belongs to F inverse Fs.
very good. Little s belongs to F inverse F S. By definition, this means pre-image of Fs, not the forward image of Fs and F inverse. So I took any S belongs to S, I have proved that guy belongs to that thing. Therefore, capital S is subset of F inverse of F of capital S. Right? I mean, what I said here, I proved it. But you need to, except the proof, you need to, even if you cannot prove it, you need to know this thing. You have to feel like that. If when you go, you take the image of A, no, this is image of O. However, there may be other things going to FA, outside A. So, F inverse of FA contains capital A always. Okay, now let's go to the other one. The other part is you to U is subset of Y. Now let's draw a picture. Here is X, here is Y, X, Y, here is U. So now you take F inverse U. You get F inverse U, you get some set. F inverse. This is F inverse U. Now you F inverse U. Now you go forward again. Then what will happen? You get the same thing? No.
It is equal to that set.
You are saying f of f equals u is equal to u. No. What do you think? You had u here, this is u. You took the inverse image of u. So it comes here. Now you are going back up. F of f equals u. Do you think it must be u?
That one is a subset of U.
Why do you say that? You are saying f of f inverse u is subset of u. That's what you are saying. Why do you say that? What's the reason?
Is it surjective something? If we say that f is not surjective, then the,
If f is not surjective, yes.
then this is true. If it is surjective, those two are equal.
If it is not surjective, why do you say it is observable?
Because there exists y in simple y in y for some x in x, fx is not equal to simple y.
Yeah, even though you struggle to tell the truth, you should tell the truth. There may be some white guys here, they are not measure one, leftover boys. So that's why when you take this here, if there are 1 or 2, 3, or whatever, they are not images of some elements in f and in x in u under f. When you take f of f inverse u, you will delete it. That's the reason. Good thing. Okay, now we claim then. Claim what f of f inverse u is subset. Can you see? What you said is very good, because most important thing is not writing the proof. Of course you have to learn to write the proofs. That's how your logical thing comes out. You have to think correctly and you said so. Okay. Now proof. What is the first line I should write?
Suppose simple u belongs to capital U.
Suppose simple u belongs to
Capital U.
suppose, let me take simple y belongs to f of f inverse u. Then I have to prove that y belongs to u, right? That's what I want to prove. If I say, suppose y belongs to f of f inverse u, f inverse u is here, I am saying y belongs to f of f, no, sorry, f inverse u is here, f of f inverse u is over there. Then if I say, suppose y belongs to this, thus there exists there is t belongs to f inverse u. I write t belongs to f inverse u such that y is equal to f of t. Do you agree? If I say y belongs to f of f inverse u, there must be some t here such that y is equal to ft. It is a trivial statement. Right? Y is equal to ft. Clearly, ft belongs to you. Why? I said clearly. I cannot write you and we in a clear way. You. Why do I say ft belongs to you? Clearly, I said. What's the reason?
By the definition of f inverse equally.
By definition of f inverse u. Actually, if E belongs to f inverse u, then ft must belong to u right away by definition. However, ft is y. Therefore, y belongs to u. Therefore, y belongs to u. Thus, I began from y belongs to f of f inverse u. I have shown that y belongs to u. Therefore, f of f inverse u is subset of u. These two results are very important. Actually, these are the things we should have spent time, but we didn't get time to spend like this. Are the other parts? What about the focus? Now, I will give you a problem. Here, find S such that it is a proper subset of f inverse fs. Over there, find capital U such that when I say capital U, then you have to find x, y, f, all of them. You have to find an example of a function f, two sets capital X and Y, and simple capital S subset of x such that S is a proper subset of f inverse fs. It's a very good exercise. Actually, I have done it. If I tell you, you all learn it. You have to think about it. Over there, the same thing. Find an example of a function f and two sets x and y, and u subset of y such that f of f inverse u is a proper subset of u. From that, you learn it by struggling. Now I don't need the answer. Because you have to think about it. You cannot say it right away. You want to say something?
We can write here it shouldn't be injective, and there it shouldn't be surjective.
Yeah, it's kind of like that, but see, if you write the example, then we learn it so we can discuss about it when you have done it. Okay, then we have this 3.4.3. I have done it also. So I get the impression you haven't done these questions, have you? No.
These questions I didn't do, but after 3 point, after next, yeah, from Cartesian products onwards I did. I got stuck with the inverse functions. And, yeah.
So you want me to do this question 3.4.3. However, I mean these are very important. If you have two sets capital A and B, f of A intersection B always is a subset of f A intersection A B. Always. I mean that's what we are proving now. And on the other hand, it is always true that f of A union B is equal to f A union F B. Is that what he is saying? You need to remember it. All right. So let's see what he says. Fx2y 3.4.3. A, B, B, F is the function of x to y. A, B, B, two subsets. So we want to show that F A intersection B. Need to show that. F of A intersection B is subset of F A intersection B. Now there is some technology in US. You don't have to erase the board. Using technology, you press some button, it cleans the board. Here I have to spend time. The reason I clean the other board is because if you have, say, A subset of B, here you have function x to y, f, A B subset of x. Then always f A is subset of f B. If A is subset of B, then f is a. Proof is also simple. What should I write first?
Let simple A belongs to
It's not a good choice of symbols.
Suppose simple A belongs to capital A.
That's incorrect. That's wrong. What is the correct one? First word is correct, suppose. Oh, assume.
Suppose Y belongs to FA.
Okay, my belongs to it. What is the next line? If I belong to FA, what do you know?
So the F inverse.
Not F inverse. I am going to prove f of capital A is subset of f of capital B.
Y is a element of FB.
How do I know? That's what I have to prove. I want to prove that I belong to FB. What can I say?
Then there exists simple X belongs to capital A such that if X equals Y.
Again, not good. Answer is correct, but symbols are not good. Then there exists. Your answer is correct. Simple A belongs to capital A. Such that Y is equal to f of A. Use always
Yeah.
to capital A is better to use simple A. Now I am on the way to prove that A is subset of B is given. I want to prove that FA is subset of f of B. So I began, assume that Y is in FA, then I am saying there is a simple A in capital A such that Y equals FA. Then what can I write? Uttara?
Since A capital is a subset of B, A is a element of capital B.
Thus, since capital A is subset of B, simple A belongs to capital B. Here you have A, here you have B. If A is here, A is in B also. What is the next step? If A belongs to B, then simple A belongs to B, then thus
Simple F of simple A belongs to F of capital B.
thus f of simple A belongs to f of capital B. But f of A is y. Therefore, y belongs to f of capital. I have written, started from y belongs to FA, I have wrote that y belongs to FB. So therefore, FA is subset of FB. This is a terribly small thing, but you need to know. I am getting the impression because we are struggling with the axioms, little things are lost, no?
Yeah.
Quite a lot of them. If you use my books, you cannot say, I mean, you use my books, but your knowledge will be better than using.
These axioms.
Yeah. Right? Now I am going to use that. I put it backside if you want to take it down or something. That's the important thing. book, according to the book, these people know these things. If they know about ordinals, no, I mean, this is not good for our class, that's my conclusion. Though we have spent 2 months, you cannot write a proof of even trivial things. We are very worried about 0 to the 0 equals 1. That's a good thing. So, I mean, it only 2 3 problems. So, can we stay here after 1:12?
I don't think so.
We can.
Yeah, I'm not sure. Seeing in this evening.
Because not many problems can be done on
Yeah. Like the ones with the functions and inverse stuff, that's better because we could do set theory questions, but this is the
When you have functions, you have trouble, no?
yeah.
Anyway, now, proof. Clear. Is it clear? I say A intersection B is subset of A. Clear? And A intersection B is subset of B. Since A, thus, f of A intersection B is subset of f of A, and f of A intersection B is subset of f of B. Now f of A intersection is subset of B, this set and that set. Hence, can I say f of A intersection B is subset of f A intersection f B? Can I? Any line not clear, you won't want to prove, but these are, I suppose, A intersection B subset of A is very clear, no? A intersection B subset of B is also clear. Therefore, f of A intersection B subset of f of A is clear, and f of A intersection B subset of f of B is also very clear. If A intersection B subset of both FA and FB, therefore, last line, if it is not clear, I can prove. But these are very trivial things. Right? Okay, there is another part for this thing. Fa minus Fb is subset of f of A minus B. Need to show that. Fa minus Fb is the subset of f of A minus B. This is what we want to prove. What is the first line here? Suppose
Y belongs to FA
Fa
minus
minus
FB.
Fb. Suppose y belongs to Fa minus Fb. Then y belongs to f of A and what?
Y doesn't belong FB.
Y doesn't belong to Fb. Since y belongs to Fa, thus there exists simple A belongs to capital A, such that y is equal to f of A. However, y does not belong into f of A. And for each simple B belongs to capital B, Y is not equal to f of B. Right? Since y belongs to fa, there is a little a in capital A such that y equals f of little a, but y doesn't belong to fb, that means no matter which b you choose from capital B, y is not equal to f of b. Still I wrote only one b. Alright. Why? Anyway, that's the other English. A belongs to relations and for each. Can this A belongs to B? Then no. If A belongs to B, then Y is going to belong to FB. Clearly, it doesn't belong to B. It comes from here. A belongs to A. If A were an element of B also, then Y samana, Y is equal to FA, so Y is going to belong to FB. Thus, simple A belongs to capital A minus B. Right? Therefore, f of A belongs to f of A minus B. I have began from y belongs to fa minus fb. I have shown that one condition is hence y belongs to y is equal to fa, no? Y belongs to f of A minus B. Thus, fa minus fb is the subset of f of A minus B. Right? Finally, we need to show that. This one clear, no? Because if we can stay here after 1:30 also, I can do some more problems. Otherwise, not enough time. Finally, we need to show that f of A union B is equal to f A union B. So these are important results to remember when you are doing topology stuff. F of A intersection B is always subset of F A intersection B, and it can be a proper subset. I asked you to find an example. When it is proper, for the case proper, and this is for the unions, it is always true. Proof. Clear. A is subset of A union B. Agree? And B is subset of A union B also. Thus, f of A is subset of f of A union B. And this and doesn't matter anything. F of B is subset of f of A union B. FA and FB are both inside F of A union B. Hence, FA union FB is subset of F of A union B. Right? Now we want to go to the other side. Right? For the converse, suppose that Y belongs to F of A union B. What this means is, hence, there is X belongs, X belongs to A union B such that Y is equal to Fx. Oh. Right? If Y belongs to F of union B, Y must be F of something in the set. I took that as clearly X belongs to A or X belongs to B, because X belongs to A union B. If X belongs to A, then Fx belongs to Fa. So Y belongs to F. If X belongs to B, then Fx belongs to Fb. So Y belongs to Fb. However, Fa, as you know, is subset of F of A union Fb. This is also a subset. So, whether you do this one or this one, however, Y belongs to Fa union. Therefore, Y is equal to Fx belongs to Fa union Fb. I took Y belongs to F of A union B. I am saying Y belongs to F A union B. Hence, F A union F of A union B is subset of F A union B. We have first shown that F of A union B is subset of F A union B and the other one. So therefore, F of A union B is equal to F A union B. That is the proof. So these are actually very elementary, but the problem is that we haven't spent time with elementary things in this class. But the question is not over by this. He is asking, for the first two statements, is it true that subset relation can be improved to equal sign? In other words, he is asking, now we have proved F of A intersection B subset of FA intersection B. Regardless of that, can I say F of A intersection B equals to FA intersection B, as well as F of A minus F of B is equal to F of A minus B? Answer is no. I am going to do it now. It is learned that